We're going to be looking for a formula for this really interesting function here. We're taking the derivative of an integral. Our integral is starting at a function g of x. It's going to a function h of x, and it's the integral of f of t dt. We know some facts about what we're looking at. First of all, f is continuous, and second of all, a g and h are differentiable. We're going to be using all of that information to find our formula, and we're also going to be using a lot of properties. So the first property that we're going to use is going to be dependent on the fact that f is a continuous function. So we're going to break this up, and we're going to use f is continuous, and I'm going to write that out. So because f is continuous, what we want to do right here is we want to break this down a little bit. This g and h, there's just too many things going on at once. So we're going to separate that into two separate integrals. Our first one is we are just going to go up to a random point between the two. Let's call it c. And actually, I want to put this on the inside. We're going to do this in two steps here. H of x, f of t dt. There we go. And just as a reminder, if we have a function that's continuous, let's say we are going from A to point B, we can find a point C, and our integral from A to B can be broken up between the two. And this is going to make our lives a lot better. Okay, there we go. So that is going to be the property that we're using here. And we are using this because f is continuous, so it allows us to do that. Next thing we're going to do is we're going to use the properties of derivatives, and we're basically going to take our dt here, and we are going to distribute it among the two bits right here. Because if we have, and I'm going to just kind of use a shorthand here, if we're taking the derivative of f plus g, this is the same thing as the derivative of f plus the derivative of g. So this is a property of derivatives. And this is going to allow us to write d dx of the integral of g of x to c, f of t dt, plus d dx from c to h of x, f of t dt. Now there's one other thing that I'm going to put in here. It's just kind of a little thing that we're going to pop onto the side here. We're going to flip this integral upside down. So property of integrals, this is a nice one to remember, is that if you have a to b of whatever function you're working with, you can put a negative sign out front and flip your bounds. And we want to have that g of x on top because of the next step. So first of all, let's actually write out what our functions look like right now. We have d dx of negative cg of x, f of t dt, plus d dx of integral from c to h of x, f of t dt. All right, last thing that we are going to do is we are actually going to be using our last step. Let's put it right here. We'll use FTC Part 1. So this is the fundamental theorem of calculus, part 1. It depends on both the fact that g and h are differentiable, as well as the fact that we have a continuous function in f. So our g of x, if we have a function equal to a to the x, f of t dt, then our FTC part 1 says we take the derivative of that function. We're just going to plug in that upper bound, that x value in there, and we're going to be done for the day. In this case, you'll notice our upper bound is a g of x. It's not just a simple x. So we are going to have to use the chain rule and multiply by g prime of x. Our negative sign stays out front. We're going to punch in that g of x, and then we're going to multiply by g prime of x. And we're going to do that for our second equation as well. We're going to punch in our h of x when we take our derivative, and then we're going to multiply by h prime of x. So this also uses the fact that, again, g and h are differentiable. So we used all of the things that we needed to, and there is our nice solution for our formula for that big integral in the first page. Thank you so much for listening.